In today's lecture, we first will talk about predictive distribution, through an example, and we'll talk about statistical inference of mean and variance. We'll start a new chapter on statistical inference of mean and variance of normal population. And that is a big chapter. So let's start with this one. Suppose you are given, I'm just explaining, you are given 60 observations and this is your data set. Okay. And assume that observations are coming from a Poisson distribution. This is your data, observed data. This is what you have. That's it. This is what you have. 1, 2, 3, 4, 5, 6, 6 rows, and each row contains 10 elements. It is coming from a Poisson distribution. Assume. And we want to make inference about the Poisson rate parameter. Assume that the prior distribution of the rate parameter is gamma 1, 1. 1 is the shape and 1 is the rate. Gamma distribution has two parameters. One is the rate parameter, another is the shape parameter. So both I took them to be 1. So the posterior distribution of theta proportional to what happens. If you recall that the likelihood part is the likelihood. So L theta is product I is equal to 1 to n e to the power minus theta, theta to the power xi over xi factorial. So it is theta to the power n theta. N is the number of observations, and theta to the power sum of xi as the power. Now sum of xi means n times x bar over xi factorial. And you have gamma prior distribution. Gamma prior distribution. So prior for theta is theta to the power 1 minus 1 and e to the power minus theta times 1. So it is say e to the power minus theta. So the posterior distribution, may I erase this part, the top part? So, okay, let me maybe write it here. Okay. So the posterior of theta is, I'm just using the notation pi to denote the posterior density function. If you prefer to use p, that is fine with me. So it is the likelihood times the prior, and it is e to the power minus n theta, and theta to the power n x bar, theta to the power 1 minus 1 e to the power minus theta. And I did not write the term product of xi factorial in the denominator because that does not involve any parameter. So I just ignored that term. I took the terms involving theta. together it is theta to the power n x bar plus 1 minus 1. I keep it 1 minus 1 because that will help me to identify the shape parameter of the gamma distribution, and e to the power minus n plus 1 times theta. So it is the gamma density, you can see clearly, gamma with shape n x bar plus 1 and rate n plus 1. So gamma in x bar plus 1 and n plus 1. So let us look at this. So in my code, I have also commented out theta density n x bar plus 1 minus 1 and n plus 1. So I want to generate data, observations from this posterior distribution. And I want to draw many observations. Suppose I sample 20,000 observations from this distribution. This is the posterior distribution, posterior sample, n times mean of my data plus 1 and rate equal to n plus 1. And then I like to calculate predictive distribution or posterior predictive probabilities. Posterior predictive probability for a new observation. So for a new observation, probability y equal to 0, a new observation y tilde, you can say it, okay, y tilde equal to 0, given the observed data is probability y tilde equal to 0 given theta times pi theta given theta integration. What is that y tilde? Y tilde is a future observation. If I know my observations are coming, observed data are coming from a Poisson distribution. When I say new observation, I'm referring that new observation is coming from another distribution. Definitely it's a discrete distribution, right? Definitely it's a discrete distribution. What is that distribution? It is obtained by integrating that theta with respect to its posterior density function. Now, given theta, given the theta parameter, new observation is also coming from the Poisson distribution. But theta is unknown. Now that theta will come from its posterior distribution. So given theta, what is the probability that new observation is 0? It is e to the power minus theta, theta to the power 0 over 0 factorial, which is 1 simply. So I just write e to the power minus theta and theta given data, d theta. This is the posterior predictive probability that a new observation is 0. Again, I can calculate posterior predictive probability of a new observation to be 1. Again, it is and for a Poisson random variable, the probability that a Poisson random variable takes value 1 is e to the power minus theta, theta to the power 1 over 1 factorial. So it is simply e to the power minus theta times theta and pi theta given data. everywhere this integration is over 0 to infinity. The parameter space of theta is 0 to infinity. One thing, it is written on your slide that if you want to do this integration with respect to the posterior density function, it is a complex distribution, and eventually you get a negative binomial distribution. And I don't want to do that integration. I will do Monte Carlo sampling. So I sampled already theta values from its posterior distribution. So I will estimate this integration through the average. So this will be, for example, estimated by 1 over n j is equal to 1 to n e to the power minus theta j times theta j, where theta j's are coming from this posterior distribution. Likewise, here it is estimated by 1 over n theta j, so on and so forth. And that is what we are doing now. So predictive probability that a new observation is 0, denoted by this notation. It is simply to the power minus theta and take the mean value over all theta. Okay. Next value is predictive probability that the new observation is 1. It is e to the power minus theta times theta, and you take the average over all of these theta values. This theta came from the posterior distribution. Keep in mind. And I can also calculate posterior predictive probability that it is equal to 2 as e to the power minus theta times theta square over 2 factorial, which is 2. So on and so forth. And you can even calculate this for any probability. So posterior predictive probability that a new observation is equal to R. R is any number from 0 to infinity. It is e to the power minus theta to the power R over R factorial. This is the Poisson probability mass function, and you integrate with respect to the posterior density of theta. So let's do that. So what did I do? So here it is this, then this my data. So you can this 1, 2, like this. You can calculate probabilities, right? For different R equal to 0, 1, 2, 3, 4, many values. But if you want to calculate it for many different values, then you can use this easier way to calculate this. This is, I calculate this function, write this function, call it f1. It is a function of the parameter, and at that parameter value, it is calculating the density function, probability mass function of a Poisson distribution. But in R, everything is called density function, irrespective of whether it is actually a probability mass function or probability density function. So in R, it is d poise that returns the probability mass function at these values 0, 1, and 2, and it is evaluated at this parameter value. Now, what I want to evaluate at all these theta sample theta values and take the average. Take the average. So first I do this, then calculate this, and now check what is the dimension of this out function. It is because I calculated this probability for 0, 1, 2, 3 different R, but it was evaluated at every posterior sample, all 20,000 samples. Therefore, it is giving me a matrix of dimension 3 by 20,000. But I want the average of all 20,000 samples. So I use this apply function, mean, and it calculates the mean. Now, you don't tell me how you remembered the syntax. You asked me that question. I remembered it because I have been using it for a long time. So don't get nervous. Even if you don't know the syntax, it is fine. Just search online. What is the syntax of averaging? Huh? That's how you get it. So you see, whether I calculate using every function writing this way or this way, you get the same answer. There is no difference. Okay. But the second option is a clever option, because if you want to evaluate for different R, let's say you want to evaluate it for R equal to 0 to up to 50, then you will not be able to write everything on your own. So it is the best way to do. So let's do that. Okay. So it is calculated. Predictive probability. Now, predictive probability, people loosely say posterior predictive probability, actual term. People sometimes say predictive probability, but both are the same thing. And I can plot this density function, right? It is plot of 0 to 50 and predictive probability. Oh, I see. What I did wrong was this. So previously, when I wrote this thing, it did not recognize. When you write within parentheses 0, 50, it does not recognize. In R, this is the syntax thing. You see, I have been doing it for almost 20, 21, 22 years, but still I'm making mistake. Okay, but I'm not ashamed of myself. The people who try, they make mistake. People who don't try, they don't make mistake. This is my philosophy. Okay, so I'm fine making mistakes, but you have to write C 0, and I want to do what? I want to plot against 0, 1, 2, 3 up to 50, and these values 0 colon 50 means like that. All right, so this is how it looks now. I will be plotting it against the observed data distribution, and then compare whether our predictive distribution, how it differs from the observed data distribution. Histogram of my data. Here, I will do probability equal to true to obtain the density curve. Probability equal to true, obtain the density curve. And x limit equal to y, x limit is not taken. In class equal to, let's say 10. Like this, okay. Or maybe, okay, that is fine. Now let us do let's see whether we can overlay the plot, one plot on the other. So if y limit is allowed, what is the issue with the x limit? Oh, I see. It has to be like this. Okay, so now it happened. And I will do up to 12. I see. And so when I write y lab x lab equal to colon, writing nothing, that means I don't want to write anything. Otherwise, it will be overlapping and not presenting any information. So now it is much nicer looking. And what you see that the predictive distribution and the observed data distribution, they are in close alliance, right? Not too much different, not too much different. But if you see the mean of the predictive distribution is towards the tail area of the data distribution, then there is a mismatch happening. That means the model, assumed model, either the model or the prior is not properly aligned with what we expect from the observed data. Because this is the model checking part. Model checking is whether your assumed model is appropriate for your observed data. Look, in this example, I have only observed data and the sample size. Sample size means you just check how many observations you have, my data. You check the length of my data. That is your N, 60, right? That's all I have. As a practitioner, I only have these observations. Then I put my assumptions, my beliefs. I assume observations are coming from a Poisson distribution. Who knows Poisson distribution is the correct distribution here? Maybe it is not. Maybe a geometric distribution is more appropriate. Maybe a negative binomial distribution is more appropriate. Therefore, we need to do the model checking. So here in all these calculation, nice things happen under the assumptions that observations are following a Poisson distribution, the prior distribution of parameter follows the gamma distribution, then I have all the nice things happen. Then I obtain the predictive distribution. Questions? Okay, so I will definitely share this code with you. So So chapter 5 is about normal distribution. What we plan to do. So the brief overview is the following. Suppose your observations x1, x2, xn are coming from this population, normal population, mean mu and variance sigma square. Your observations, that means x1, x2, xn are known, and you assume underlying distribution is normal with mean mu, variance sigma square. Mean mu and variance sigma square, they are unknown parameters. We want to make inference about them. So the first thing we'll do, assume sigma square is known. Make inference about mu. And the second thing, we do not assume sigma square is known. Then make inference about both mu and sigma square. So this is the learning thing for chapter 5. One by one. So we say assume y1, y2, yn. Sometimes we denote x1, x2, xn as our observed data. Sometimes we use the notation y1, y2, yn as the observed data. But basically, these are n observations coming from this distribution, IID observations, normal distributions. So what is the joint density function, or you can say likelihood function of the based on the data? So it is the density function, normal density function evaluated at yi, y1, y2, yn, and take the product over I. Now, if you take the product, after simplification, what happens? This first term is a constant term. So it raised to the power n over 2, and I can write it 2 pi sigma squared to the power minus n over 2, because it was in the denominator. And the exponent part, when you take the product, the power of the exponent becomes the total. So here it is the sum of yi minus mu square over sigma square. So we call it Q, this guy. So Q is this guy, Q over 2. And we can write this Q nicely in terms of these two quantities. One is S square, another is y bar minus mu square. How? This is little bit of calculation, little bit. So this one, we have xi minus mu square. I can write it as xi minus x bar plus x bar minus mu square, added and subtracted. This is a plus b square formula. It is a square plus b square plus 2ab. And the summation sign is right at the front. Now, when you have the summation sign in front, you take the summation before each of the terms separately. So you have this sum, then you have this sum, and then you have this sum. Now, look at the third term. Third term is a product of three terms. One is 2, another is x bar minus mu, another is xi minus x bar. 2 is a constant, so I can take outside of the summation sign. X bar minus mu is also a constant, does not depend on I. So I can take it outside of the summation sign. The remaining part is xi minus x bar, sum. So I can write this guy, entire thing, as 2 x bar minus mu, and sum of xi minus x bar means x1 minus x bar plus x2 minus x bar now x bar is x1 plus x2 plus xn divided by n. So n x bar is equal to x1 plus x2 plus xn. So the total of observations is n times x bar. So here, how many x bars you have? You have n x bars. And if I collect the first terms, it is x1 plus x2 plus xn. So it is x1 plus x2 plus xn minus n x bar. Because of this result, it is 0, big 0. So the cross product term goes away. Now look at the second term. Second term, x bar minus mu squared, sum over I is equal to 1 to n. The summand does not depend on I. It's a constant term. So constant term, if you sum n times, it is n times x bar minus mu squared. So I can simply write it as n x bar minus mu squared. And remember, what is the sample variance formula? Sample variance square is sum of xi minus x bar squared divided by n minus 1, right? We always calculate sample variance. I give you a bunch of observations. I can ask you to calculate average x bar. Sample variance is this guy, xi minus x bar squared sum divided by n minus 1. So the first term is n minus 1 s squared, and the second term is n x bar minus mu squared. And if you look at Q was sum of xi minus x bar squared, xi minus mu squared over sigma square. So it is n minus 1 s squared over sigma square plus n x bar minus mu square over sigma square. Okay, now this is that's the only thing. So this is how it is written. Q is written in that format. Now, why did I do that? I'll tell you now in the next page. Why I, instead of keeping everything xi minus, I'm actually interchanging xi and yi, but in the slide, I'm using yi. But when I explain it, by mistake, I use notation xi, but they are the same thing. If you go to a literature class and tell people, hey, xi and yi are the same, what would happen? They'll tell me, go back to kindergarten and learn X, Y, A, B, C, D first. Okay, so first I assume sigma squared is known, mu is unknown. inference on mu. So if I want to make inference on mu, then I need to look at the likelihood, the part of the likelihood that involves mu. And the part of the likelihood that involves mu is this guy. Let's go back here. So I want to make inference about mu. So posterior distribution of mu given the data will be the likelihood function mu given data times the prior distribution of mu. I assume sigma square is known. So what was the likelihood of mu given data is proportional to 2 pi sigma square n over 2 e to the power minus normal likelihood, right? Normal distribution likelihood function. It was xi minus mu square over sigma square. And we wrote this. So sigma square is known. I assume sigma square known. So which part will contribute to the posterior distribution of mu? Which part of the likelihood will contribute to the posterior distribution of mu? Only this part, right? Therefore, I wrote this is proportional to e to the power minus n x bar minus mu square over 2 sigma square. And you see, all the reasons of this breaking up xi minus mu is that for this simplification, if I had kept xi minus mu square, then I had a very complex quantity. But after this breakup, everything is in terms of x bar. X bar is the sufficient statistics for mu. Sorry, again, I used X notation, but it should be Y bar. So data, you can denote it by X1, X2, Xn or Y1, Y2, Yn, whichever you like. So here you have n over 2 sigma square mu minus Y bar square. So this is the likelihood contribution, and a normal prior is a conjugate prior. So if I assume mu follows a normal distribution with parameter mu 0 and sigma 0 square, then the posterior density of mu will be proportional to this guy plus this guy, proportional to this. But still, in order to show that, so it's a good thing, okay? Good thing that we have this structure, but can you tell me what is the actual distribution of mu the posterior distribution of mu? By looking at the kernels, you can identify that it is a normal distribution. Exactly. Why? Because you can express this guy as a negative of a quadratic form in mu, and that is the kernel for a normal density function. So little bit of general idea, which will help you in lot of calculations. I was telling to the other class that normal distribution is the mother of all distributions. Chi-square distribution, F, T, Rayleigh, whatever you call, they are children of normal distribution. But normal is the mother. And if we can write some density function or distribution in the normal distribution, then you know how to do the integration. All the calculations are known. So normal distribution has this general structure. So if you have the density that is of this form, ax minus b squared, a positive, b is in the real line. That means this x, the random variable x, follows a normal distribution with mean parameter equal to b and variance equal to 1/2a. So it's a quadratic form in x, square form in x, and it must be associated with the negative sign in the exponent. If it is not associated with the negative sign, then you cannot do the integration. It is not a density function. So this is important. A must be positive. Now, look at the slide here. We have this density function. We have written in this format proportional to this times this, and our job is to figure out the density function of mu in the form of a normal kernel. So I should be able to write it as e to the power minus a times mu minus something square. My job is to figure out that a and b for mu. So here it is given, look, I write this entire thing, this plus this, without 2 in the denominator, as n sigma square mu minus y bar square, and 1/sigma 0 square mu minus mu 0 square. Okay. Now I can write this as a times mu square minus 2b mu plus c. A is the term collecting all the coefficients of mu square. So you get n/sigma square from here and 1/sigma 0 square. That is A. 2b mu is the term involving, these are the coefficients involving mu. okay? And C is the constant term. Now what I do, I want to complete the square. So take A outside. So I take A outside here, and then write mu minus B over A, square of it, okay, plus C tilde. C tilde is another constant. So this part, do you get it? C tilde. So V is equal to N over sigma square and mu minus Y bar square. And the other term is 1 over sigma 0 square mu minus mu 0 square. Okay, so it's in the next class, next lecture, I'll derive this one and show you that it follows the normal distribution.